Hi, my name is Robert Overholt, and this is my physics extra credit video, and we're looking at the world's largest rope swing. If you haven't seen the video, you definitely need to check it out. It's pretty cool. And we're going to look at some of the physics behind that video. So we're going to make some assumptions right off the bat. First off, we're taking away air resistance. I know that's definitely a reality, but for the sake of making predictions, we're going to leave that out. So no air resistance. The mass of a jumper, we're just taking the mass of an average male, which is about 70 kilograms. And then we calculated this spring constant of about 963, but we're going to leave the calculation out of the video for now, just for the sake of time. And then we know from the video that the height of the arc is 42.67 meters. The length of the rope is about 40 meters. And when the jumper is at a vertical, he's still going to have a cushion of 10 feet, which is good because otherwise he might be in trouble and that rope swing won't be very much fun. First off, the speed of the bottom of the swing. We know delta E is going to equal to 0, so we can just set final to initial energies. U final and kinetic initial can both cancel out. So we're left with 1/2 mv squared equals mgh. We're going to plug in the values and get about 30 meters per second, which that guy is moving, so sounds like fun. Tension force at the lowest point, we're going to use this perpendicular force and then add it to gravity. So when you plug it in, this is the length of the rope that we were given, and we're going to get about 2,163 newtons. Next, we're going to find the velocity at a 30-degree angle. So when this guy's at 30 degrees from the vertical, we want to know how fast he's going. So first off, we have to solve for the height. So that involves a little bit of trig, and then we're plugging it into the formula, 1/2 mv squared plus mgh. So that's final essentially equals initial, and we're going to cancel some stuff out, masses, and then solve for v and get about 27 meters per second. Next, we are going to look at the tension force at when this guy's at a 30-degree angle. So how tight is that rope when he's at a 30-degree angle from the vertical? So to do this, we're again going to use this F perpendicular and then add it to mg over cosine theta. So that again takes into account this angle and then gravity, the force of gravity. And then when we plug that in, we get 2,084.89 newtons. And when we compare that to the force of tension when you're at the bottom, it makes sense because obviously the force of tension at the bottom is going to be much greater, which will come into handy a little later when we are finding out the stretch. So we'll be looking at that a little later. So like now, what is the stretch of the rope at the bottom of the swing? We're going to plug in the force of tension that we calculated when it's at the bottom, and then this spring constant that we calculated, that we're not going to go into detail because it's got a little bit of calculation and manipulation to it. Or you can look it up like a climbing constant. But for now, we're just going to use 963 and plug that in, and then we find out that this rope is going to stretch 2.25 meters, which makes sense. I mean, you're going pretty fast. It's a pretty big rope. So now we're going to find the stretch of the rope at a 30-degree angle. So in this case, again, we're going to use this perpendicular force, and then the gravity in relation to that angle, and then this formula 1/2 kx squared. And then we're solve for x, and we get 1.64 meters, which should be smaller at an angle because the tension force is the largest at the bottom. So yes, this is realistic. This is good. And then we made a model to simulate this. Again, we put in all the values that were given and that we calculated, and we get this model for the spring. We also gave the jumper a little bit of z velocity initially because he does jump off of the ledge. So that kind of explains why it's not a uniform pendulum motion. So again, we're neglecting air resistance, and so yeah, that is the model. Thank you for watching. I hope you learned a little bit about that video, and yeah, thanks.